Hi everyone, this is Lilith. I'm one of your IAs for BIBC 102. And in this video, I wanted to quickly go over the energy diagram and how the energy diagram changes when there is an enzyme added to the reaction. So this is your energy diagram. As you can see, I've already populated it with many words and symbols and arrows. So make sure I go over everything here so you understand it easily. So let's look at the y-axis. On the y-axis we have the free energy that's denoted in G. And on the x-axis we have the reaction coordinate. You can think of the reaction coordinate as the pathway the reaction takes to go from substrate, transition state, to product. As you can see here, we have the substrate, also called the reactant. Then we have here the transition state, or the double dagger, which is what that is called. Then at the end over here, we have our product. Now, what's important about G is that it tells us, essentially, if our reaction is spontaneous, if it's favorable. And how does that tell us that? As you can see here, our substrate or reactant is at some kind of level of energy, right? Let's say it is at, here I can choose green, no, not green, red. Let's say S is at G1. That's its energy state. Now look over here. The product is at a different energy level. Let's say that the product is at G2. Over here we can see that the difference between G1 and G2 is negative. And that difference in the free energies of S and P is called delta G. And that makes sense because if this is G and that's G, then delta G would be the difference between them. When your product is at a lower energy state, as in your delta G is negative, your reaction is going to be what's called exergonic. And that means that your reaction is spontaneous. For a reaction to be spontaneous, it means that the reaction is favorable to occur. Okay? Now, let's think of it like this. What if our reaction, or we want to run the reaction backwards? What if we want to go from product to substrate? Well, I guess I would have to explain the transition state before we get there. So let me talk about the transition state. The substrate wants to get over here, right? You see how it has to climb this energy hill. That means it needs this much energy to get to the transition state. And that energy is this. It's called the activation energy. And the phrase activation energy kind of speaks for itself, right? Activation energy, the energy needed to activate. And this is where our substrate is slowly becoming our product. So you can think of that as the activation point. And so this is the energy we need to get to the activation. Then, after having a transition state, after having a double dagger state, the molecule loses energy, or it comes down the energy ladder to get product. Now, what if we wanted to go back? The product molecule would have to climb an even higher energy ladder, right, than it was over here, to be able to get to the transition state. So that tells us that the reaction that's going this way from substrate to product is spontaneous because its hill, its climbing, is smaller than its downfall. However, going up this way is bigger than coming down this way. That means the reaction from product to substrate is non-spontaneous. And in this case, product to substrate, the delta G between that is positive because this is lower and this is higher. So, in short, If your delta G is negative, then it's spontaneous. If your delta G is positive, then it's non-spontaneous. And we will cover this in the lecture further. Another thing before I move on to enzymes. The activation energy is also called delta G double dagger. Make sure you don't mistaken or make sure you don't get confused between this G, and this G, right? This is just the energy, the free energy state of the substrate, the transition state, or the product. Delta G, and I believe Professor Hampton mentioned that it's actually delta G prime, so there you go. Delta G prime is the difference between the energy states of substrate and product. And delta G double dagger is just another name for activation energy, and that's right here. Okay, enough of that. What if we add an enzyme to the reaction? As you saw in the lecture slides, the enzyme looked something like this. I'll draw it over here. It is a protein, right? Let's say something like this. And it has catalytic activity, meaning it speeds up reactions. And how does that speed up reactions? Let's say we have some kind of a molecule here that it holds inside of it. It speeds up the reaction by taking this transition state and stabilizing it. And when it stabilizes this transition state, the activation energy that needs to that the substrate needs to get over this hill decreases. Meaning, think of two, let me change my colors. Think of, here we go, purple. One person here, right? And another person here. I need to make that person a different color. And think of this red person. The pink is, or the purple, is gonna go all the way this hill and then come down to get to the product, right? And it's gonna take it a longer time to do that. But this red one, or coral, I don't know what color this is, it travels a smaller distance, right? If we're talking about people walking. So that's evident how the addition of an enzyme and the lowering of the activation energy speeds up our reaction. Okay? And let's see what else I wanted to cover. Okay, another very important point. The activation energy is lowered, right? And the rate of the reaction going from substrate to product is increased. However, the rate is increased to the same magnitude as it is going from product to substrate. If you look at it, before it took the product all the way this much to get over the hill, but now it takes it only this much to get over the hill. So the activation energy was decreased. Oh shoot, sorry. The activation was decreased this much for the forward reaction, and again this much for the backwards reaction. So the rate is switched to the same magnitude for the forward and backward reaction. What do enzymes not do? Enzymes do not mess with the ground states of the substrate and the product. And how do we know that? Enzyme or no enzyme, doesn't matter. Our substrate starts over here and our product ends over here. And our delta G prime is always the same, no matter if there's an enzyme or not. The only thing that the enzyme changes is the stability of the transition state, makes it more stable, and the activation energy. It lowers it. Okay, it looks like that's all I have for this short video. Thank you for listening, and always don't hesitate to email me if you have any further questions or if you have any suggestions for future videos. Bye!